I'm responsible here at Accure for our product and our customer-facing projects. I've been working with batteries for now roughly a decade. At Accure, we're doing battery analytics, so working with batteries that are actually operating. I would say before I joined Accure, I had a lot of fun with building batteries and not really seeing them perform in the field. So it's very interesting to look into both. Yeah, since 4 years, I'm now looking into everything field data related, and that's also why SOC and the accuracy of it is, yeah, very often a topic we need to tackle. So, yeah, I think actually I'll start with the talk because actually I have a lot of slides and planned for 30 minutes of presentation, but I want to give you the option to Q&A. Actually, we're not so many people, so if you have a question like in between, feel free to just jump in and ask. Yeah, happy to discuss it. So let's start. What is Accure? So I have to do that briefly, of course. We're a predictive battery analytics platform. We're basically turning raw battery data into actionable insights. We are using for this physics-based models, semi and empiric models, and we are using this combined with an AI approach to basically get the most out of your battery. So on-site systems are pretty good at operating the system in the moment of use, but we're trying to dig deeper, and our predictive battery analytics platform analyzes data over time and across fleets, and therefore we are able to identify issues early, spot long-term trends, and basically help you to improve the performance of your battery system, get more revenue out of it, and run it in the safest possible mode. We have supported more than 80 gigawatt-hours globally, and we have teams located in the US, in the UK, and Australia, and we are headquartered in Germany. That's where I'm from. Probably you can spot it from my nice accent. So we have gathered some insights about the batteries we are monitoring, and we put all this into a nice little report, the energy storage health and performance report. So if you're interested, it's free out there. You have this QR code. You can just scan it and download it. We've looked over more than 100 commercial operating BESS sites and identified some very interesting things. I think a lot of the stuff is pretty interesting because the spreads are wider than I would have expected it, and the number here at the bottom, the plus minus 15% SOC errors that are common in LFP batteries. This is like the talking point today for my talk. So briefly, probably a lot of you know a lot about SOC. I'll give you the intro anyways. So if the whole audience is for skipping this, let me know. Otherwise, I'll proceed. So normally, non-LFP batteries have something like a inaccuracy for the state of charge of something between 5 and 10%. You're using a safety margin to basically limit your operating range. For LFP batteries, that's normally some more, so something between 10 and 20%. So you basically cut that off at the top and at the bottom and limit your depth of discharge in a way. So what are the consequences of this? You normally you need to apply those safety margins, because otherwise your trading decisions will be pretty bad, and you will miss market opportunities, or you risk to pay fines, basically because you cannot deliver on the power and or energy that you are up to. So this normally translates to some opportunity cost in terms of revenue. If you're interested to learn exactly on how this translates into revenue losses, here's another read from us. Our CTO basically wrote an article how the accuracy of an SOC can exactly impact your revenues. But today I'm going a bit deeper into how SOC is actually estimated, and therefore we're going through 3 different methods briefly, and then I'll add the perspective of cloud analytics. So the point will be first Coulomb counting, voltage, then the voltage method, and the third piece is battery, the capacity degradation that occurs in the battery, and what the impact on the SOC estimate is in this regard. So 2 things: what are the challenges there, and how does cloud analytics address those? So first, Coulomb counting. Probably a lot of you have already heard that term. Here you can see a real-world example of a 80 megawatt-hour LFP system located in North America. We're looking here at a 30-day time interval. At the top, you can see the current in amp, so basically charge and discharge profiles. You can see nothing too spectacular. Just charging, discharging. And at the bottom, you see the SOC estimate based on Coulomb counting. So as you can see here at the in the earlier phases, like day 1, day 2, it's like looks all right. It's basically no huge problem. The SOC looks like it's going from 100% to nearly 0. We're doing the cycles, but this is basically drifting away. So why does the BMS struggle here? You have limited memory and processing capabilities. So how does it normally work? You're measuring, you're calculating, you're overwriting, and so forth. So you're basically progressing your error through the system. And this then translates to a pretty significant error in the SOC estimate, which is in this case 20 up to 20% after only 2 weeks time. And as you can imagine, if you're relying on that SOC to trade your energy, that is not a good thing. So you need to recalibrate at certain points. So how can battery analytics help with this? So we basically don't have those limitations. So we can analyze the whole time series, and we have memory in the cloud. So we basically just set off those effects that will make your SOC drift away, so that you can basically rely on that SOC. And as you see, it's really just that dynamic offset here in the signal that does it. So there's basically Coulomb counting. Pretty standard method, pretty easy to correct. Next thing is the voltage method. On the left-hand side, you can see you can see an OCV curve of an lithium iron phosphate battery. It's OCV means open circuit voltage, so you're just going from a specific voltage to some state of charge. So you're just measuring it under open circuit conditions, and then you get your SOC. That's pretty nice. The concept is pretty simple. You can provide some recalibration points out of this for your Coulomb counting. So what are the challenges here? So the OCV curve is pretty flat for LFP. Not everywhere, but in several areas. So here you can see, for example, this part between 40 and 55% is very, very slow and translates in a very narrow voltage signal. So you have in your BMS, you normally have errors in terms of measuring the voltage of the different cells. And if it's so narrow, you basically don't know where you end up. And to give you like a comparison, an LFP OCV curve is roughly 3 times flatter than NMC than an NMC one, and yeah, at least 3 times harder to predict based on that. So you can predict the volt based on this voltage method. I would say at certain points very well where you are in terms of state of charge, but there's unfortunately another electrochemical effect that makes this hard. The effect is called hysteresis, and yeah, it makes things worse because if you apply that open circuit voltage, so you charge, you wait for a moment that everything settles, and then you measure, it basically depends on if you're charging or discharging on what curve you will end up. So it kind of has a the history of the charge or discharge in mind. And the result is that you have multiple OCV curves, not a single one. And the position, especially if you're cycling back and forth, of course, changes. And in this you can see that the gap between the charge and discharge can be pretty significant. So here you have 36 percentage points that are between those two measuring points. And if you're doing something like frequency control reserve or just some frequency services where you're basically switching your mode of operation back and forth pretty rapidly, you can imagine that the BMS gets confused rather quickly, and that this is actually a problem in the real world. I'll show you an example in the next few minutes. But you can imagine that you don't want to be in those areas, or you try to avoid this, because otherwise something like this happens. Here you can see on the top charge again. At the bottom, you see the SOC. Here at a certain point that is marked, the BMS will basically recalibrate. So till here, everything was pretty fine. Like you have the SOC, there's a minor deviation. You're just going through the hours, and here at hour 21, something like that, the system recalibrates because it just thinks it is somewhere else, and then you create this significant offset that you are pulling through the whole system till you end up at a very high SOC again. So that's something you want to avoid. But how do you avoid it? There is basically a way to model this hysteresis effects. So a BMS cannot do this normally because the processing power and its memory is short, because it's meant to calculate everything in milliseconds. It cannot run complex battery models because of that, and therefore eliminating the hysteresis is very, very difficult. So with some more calculation power in your back, you can basically run a hysteresis submodel and mimic the effects that happen when you're going through this charge and discharge cycles. So you're generating kind of a submodel that will have still some areas where the confidence is moderate, but the overall confidence is way higher than a simple voltage model itself. And you can then use the different confidence areas basically to weigh in into your calculation, and therefore generate over time an even more accurate model of that whole system. So the takeaway here is you can add this kind of models to basically increase the accuracy of your SOC calculation. The third effect that I promised you in the beginning is basically degradation. Everyone knows that batteries degrade. The degradation is normally not as bad as some people anticipate, especially in the beginning. Everyone was fearing, like, I would say, aging curves over 3% per year. That is not the point. But as you can imagine, this state of charge references to specific answers of the electrochemical system based on the capacity. And if the capacity changes, so will your mapping change between the SOC and the voltage points, basically. And here you can see an example. Again, a small BSS in long-term operation. I think residual capacity was around 80%, and we needed to identify why this was happening. Like, the SOC was drifting away significantly. And the root cause was pretty simple, and it's not always that simple, to be honest. But this one here is pretty nice to see. The BMS just assumed nominal capacity, 100%. And as you can imagine, you're operating your battery over a 10, 15, 20-year time frame, and battery engineers that are building those systems, they will test the battery. They will give it like a few hundred cycles in the lab, and then everything gets extrapolated on this. And based on this, you get the results in your BMS. So you have lookup tables and stuff like that basically look into this, into these aging effects. And you can imagine that the older the system gets, the worse your assumptions get. And you will not be able to spot this kind of behavior during your factory or site acceptance testing, because the battery is still fresh and it's perfect to go. It's probably the SOC calculation in your testing will work very well, but you can also imagine that if you have, after 6 or 7 years, this kind of behavior, your optimizer or your trader will have a hard time to basically estimate battery states in the right kind of fashion. So what can we do with cloud analytics? It's very similar to the points before. Our models basically account for this. So we have we have historical data and we have rather high computational power. And in combination, we can basically get rid of those effects and wipe them out completely. So at this point in time, you're probably asking yourself, okay, that's interesting. I can get a nice SOC from Accure, but when I know it, how does my battery know? And I basically want to go to the application now. And for this, a very brief breakout. Worldwide, there are two dominant revenue streams for BESS. One is arbitrage wholesale, and the other one are dynamic services. And it doesn't really matter if it's a D-Star service from the UK or an frequency control reserve from Germany or some other services from anywhere else. It's basically dynamic services. Your asset is needed to keep the grid stable, and it will provide some energy or be there for a case of emergency. Or there's the arbitrage kind of wholesale where you're aiming to buy electricity cheap and discharge your battery when market conditions are better. So energy is more expensive and you make a share from this. So we now think about this. Okay, I have a BMS that has some limitations when it comes to SOC. How does it? What am I doing? So what normally is done, and here on the left-hand side, it's you remember this from the beginning. It's you're putting limits on this. You say, okay, there's a hard limit, a soft limit, there's some error buffer, you name it. So you basically make your depth of discharge smaller so that you do not run into trouble when you are discharging for half an hour or charging for 2 hours or something like that. And one solution that you could apply would be, and we're also providing dashboards. So you could use the dashboard and look into, okay, what happened? What would have been a good would have been a good limit yesterday or the day before, based on availabilities, based on the different assumptions. But this does not really help you in terms of making good decisions in for the future, because your current SOC will be influenced by factors that are occurring during charge and discharge phases. And when you're revenue stacking and operating in different kind of services, and you're doing an hour in wholesale and 30 minutes in some kind of dynamic service, then you want to know how you can add up those services. And a limit that just switches at some point in time that you don't know is basically not very good to make informed decisions in the future. So you're risking that you have old signals, and you basically run into the same troubles you have with fixed limits. So looking backwards doesn't help you to trade forward. Then you could think, okay, limits that come from a dashboard, maybe they need to come directly to my trader. So you have a battery, you have your analytics platform, and then there are some dynamic limits that are provided to the trader, the optimizer, the one who's doing the bits. And this will help you with the immediate next decision of what you can do. And but it keeps the same problem. You cannot stack different services over each other, because this dynamic limit would at some point change, and then you cannot schedule several blocks over each other. So you cannot really anticipate how the SOC error will change over time, and therefore you are basically remaining in an area that is pretty opaque. So it's better, but still pretty short-sighted. And what, from our perspective, is the best way to do it is an dynamic SOC correction. You basically gain full transparency. So you correct the SOC, or sometimes also the energy value, but kind of interchangeable if you have the values. You add all the effects in there that are presented to you earlier. And this basically enables for you a forward-looking estimate where the system will, where you know where the system will be after you did your service 1, and then you can add your service 2. So basically, you're doing the same kind of trading decisions that you did before, but you can reduce your error margin because you know exactly where the system stands at the moment. And this basically enables that you can get 3, 4, 5, 6, sometimes over 10% more revenue out of a system. So what are the 3 key takeaways? Number 1, an accurate SOC drives revenue. So even small estimation errors can lead to a lot of missed opportunities or make you pay pretty hefty fines. Cloud analytics outperforms BMS in a lot of different ways. It's definitely an add-on, so you need some of the BMS functionalities on site, and the critical points you can advance your BMS there. And the forward-looking SOC, that's what I presented last, is essential to increase your trading success, because you can build your models as you're used to, without having the need to kind of correct any buffers or limits or anything else. So I think I have now roughly 5 minutes left, and would open this to discussion.